formula for calculating voltage drop in parallel conductors is voltage drop equals resistance per unit length times current times length divided by the number of conductors per phase. In this formula, voltage drop is measured in volts. Resistance per unit length is the resistance of a single conductor per unit length, measured in ohms per meter. Current is the current flowing in the circuit, measured in amperes. Length is the length of the circuit, measured in meters. Number of conductors per phase is the number of parallel conductors used for that phase. In parallel circuits, the resistance is effectively reduced by the number of parallel paths. Therefore, the total resistance of the parallel conductors is calculated as total resistance equals resistance per unit length divided by the number of conductors per phase. Using Ohm's law, the voltage drop is then calculated as voltage drop equals total resistance times current times length. Substituting the total resistance formula, we arrive at the initial voltage drop formula. For example, consider a scenario where there are 4 conductors per phase, each with a resistance of 0.1 ohms per meter, carrying 100 amps for a distance of 100 meters. The voltage drop would be calculated as follows: voltage drop equals 0.1 ohms per meter times 100 amps times 100 meters divided by 4, which equals 2.5 volts. It's important to note that this formula assumes the current is evenly distributed among the parallel conductors. For unbalanced loads, the voltage drop will vary across the different conductors. To further elaborate on calculating voltage drop with parallel conductors, let's delve into some key concepts and considerations. Firstly, understanding the properties of conductors is crucial. Conductors, typically made of copper or aluminum, offer a path for electrical current to flow. Each conductor has a specific resistance, which opposes the flow of current. This resistance is influenced by the material's resistivity, the conductor's length, and its cross-sectional area. Secondly, when conductors are connected in parallel, the overall resistance of the circuit decreases. This is because the current has multiple paths to flow through, effectively widening the pathway and reducing the opposition to current flow. The more conductors you have in parallel, the lower the overall resistance becomes. Thirdly, voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. As current flows through the conductor, some of the electrical energy is dissipated as heat, leading to a decrease in voltage at the end of the conductor. Excessive voltage drop can negatively impact the performance of electrical equipment, causing them to operate inefficiently or even fail. Fourthly, consider the impact of conductor length. Longer conductors have higher resistance, leading to greater voltage drop. This is because the current has to travel a greater distance, encountering more opposition along the way. Therefore, it's essential to minimize conductor length whenever possible to reduce voltage drop. Fifthly, the current flowing through the circuit also plays a significant role in voltage drop. High currents result in greater voltage drop due to the increased energy dissipation in the conductor. Therefore, it's important to select conductors that are appropriately sized to handle the expected current load without excessive voltage drop. Sixthly, the formula provided earlier assumes that the current is evenly distributed among the parallel conductors. However, in real-world scenarios, this may not always be the case. Factors such as variations in conductor length, termination quality, and conductor impedance can lead to unequal current distribution. Seventhly, when dealing with unbalanced loads where the current is not evenly distributed among the phases, the voltage drop will vary across the different conductors. In such cases, it's necessary to perform a more detailed analysis to determine the voltage drop in each conductor. This may involve using circuit simulation software or applying more advanced calculation techniques. Eighthly, to mitigate voltage drop in parallel conductor systems, several strategies can be employed. One approach is to increase the size of the conductors, which reduces their resistance and allows them to carry more current with less voltage drop. Another strategy is to use conductors with lower resistivity, such as copper, which offers less resistance than aluminum. Ninthly, proper installation and termination techniques are also crucial for minimizing voltage drop. Ensure that all connections are clean, tight, and free of corrosion to reduce contact resistance. Use appropriate connectors and tools to ensure a reliable and low resistance connection. 10thly, regular maintenance and inspection of the electrical system can help identify and address potential voltage drop issues before they become major problems. Check for loose connections, corroded terminals, and damaged conductors, and take corrective action as needed. 11thly, the National Electrical Code, or NEC, provides guidelines for conductor sizing and voltage drop calculations. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Consulting the NEC and other relevant standards can help ensure that electrical systems are designed and installed to minimize voltage drop and operate safely and efficiently. 12thly, in practical applications, voltage drop calculations are essential for selecting the appropriate conductor size for a given load and distance. By calculating the expected voltage drop, engineers and electricians can ensure that the electrical equipment will receive the proper voltage for optimal performance. 13thly, voltage drop calculations are particularly important in long circuit runs, such as those found in industrial facilities or large commercial buildings. In these situations, the cumulative effect of voltage drop can be significant, potentially leading to equipment malfunction or failure. 14thly, when performing voltage drop calculations, it's important to consider all relevant factors, including the conductor material, size, length, current load, and operating temperature. These factors can all influence the resistance of the conductor and the resulting voltage drop. 15thly, software tools and online calculators are available to assist with voltage drop calculations. These tools can simplify the process and provide accurate results based on the input parameters. However, it's important to understand the underlying principles and assumptions of these tools to ensure that the results are valid and reliable. 16thly, in addition to the voltage drop formula provided earlier, other methods can be used to calculate voltage drop in parallel conductor systems. One common method is the use of voltage drop tables, which provide pre-calculated voltage drop values for various conductor sizes and current loads. 17thly, another approach is to use circuit simulation software, which allows for a more detailed analysis of the electrical system and can account for factors such as conductor impedance, load characteristics, and imbalance conditions. 18thly, when selecting conductors for parallel applications, it's important to ensure that they are of the same material, size, and length. This helps ensure that the current is evenly distributed among the conductors and minimizes the risk of unequal voltage drop. 19thly, it's also important to consider the ampacity of the conductors, which is the maximum current that they can safely carry without overheating. The ampacity of a conductor is determined by its size, insulation type, and ambient temperature. 20thly, the NEC provides ampacity tables that list the allowable ampacities for various conductor types and sizes. It's essential to select conductors with sufficient ampacity to handle the expected current load without exceeding their rated capacity. 21stly, in some cases, it may be necessary to derate the ampacity of conductors due to factors such as high ambient temperatures or the presence of multiple conductors in a conduit or cable tray. Derating factors are provided in the NEC and should be applied as necessary to ensure that the conductors are not overloaded. 22ndly, when installing parallel conductors, it's important to follow the manufacturer's instructions and the requirements of the NEC. Ensure that the conductors are properly supported and protected from physical damage. 23rdly, it's also important to maintain proper spacing between the conductors to allow for adequate ventilation and prevent overheating. 24thly, regularly inspect the parallel conductor system for signs of damage, corrosion, or overheating. Address any issues promptly to prevent further damage or potential hazards. 25thly, consider using thermal imaging to identify hotspots in the electrical system. Hotspots can indicate loose connections, overloaded conductors, or other problems that can lead to voltage drop and equipment failure. 26thly, implement a preventative maintenance program to ensure that the parallel conductor system is properly maintained and operating efficiently. This program should include regular inspections, testing, and cleaning of the electrical equipment. 27thly, voltage drop can also be caused by inductive reactance, particularly in AC circuits. Inductive reactance is the opposition to current flow caused by the inductance of the conductors. 28thly, inductive reactance is proportional to the frequency of the AC current and the inductance of the conductors. Longer conductors and conductors with larger spacing have higher inductance and therefore higher inductive reactance. 29thly, to minimize inductive reactance, it's important to keep conductor lengths as short as possible and to minimize the spacing between conductors. 30thly, using twisted pairs or bundled conductors can also help reduce inductive reactance. 31stly, capacitive reactance can also contribute to voltage drop, particularly in long cable runs. Capacitive reactance is the opposition to current flow caused by the capacitance of the conductors. 32ndly, capacitive reactance is inversely proportional to the frequency of the AC current and the capacitance of the conductors. Longer cable runs and cables with higher insulation dielectric constants have higher capacitance and therefore lower capacitive reactance. 33rdly, to minimize capacitive reactance, it's important to use cables with low dielectric constants and to avoid long cable runs. 34thly, power factor is another important factor to consider when calculating voltage drop in AC circuits. Power factor is the ratio of real power to apparent power and is a measure of the efficiency of the electrical system. 35thly, low power factor can lead to increased current flow and therefore increased voltage drop. Improving power factor can reduce current flow and improve the efficiency of the electrical system. 36thly, power factor correction can be achieved by adding capacitors to the electrical system. Capacitors provide reactive power, which offsets the inductive reactance and improves the power factor. 37thly, harmonic distortion can also contribute to voltage drop in AC circuits. Harmonic distortion is the presence of non-sinusoidal waveforms in the electrical system. 38thly, harmonic distortion can be caused by nonlinear loads, such as electronic devices and variable frequency drives. Harmonic currents can increase the current flow in the electrical system and therefore increase voltage drop. 39thly, harmonic filters can be used to reduce harmonic distortion and improve the efficiency of the electrical system. 40thly, it's important to regularly monitor the voltage levels in the electrical system to ensure that they are within acceptable limits. Low voltage can indicate excessive voltage drop, while high voltage can indicate other problems, such as overvoltage or undervoltage conditions. 41stly, voltage monitoring can be performed using a variety of instruments such as multimeters, voltage recorders, and power quality analyzers. These instruments can provide valuable data about the performance of the electrical system and can help identify potential problems. 42ndly, it's important to keep accurate records of voltage drop calculations and measurements. These records can be used to track the performance of the electrical system over time and to identify trends that may indicate potential problems. 43rdly, regularly review the voltage drop calculations and measurements to ensure that they are still valid and accurate. Changes in the electrical system, such as the addition of new loads or the modification of existing circuits, can affect the voltage drop and may require recalculation. 44thly, consider using a voltage drop calculator to simplify the process of calculating voltage drop. Voltage drop calculators are available online and as software applications. They can help you quickly and easily calculate voltage drop for a variety of different scenarios. 45thly, when using a voltage drop calculator, be sure to input all of the relevant parameters accurately. The accuracy of the voltage drop calculation depends on the accuracy of the input data. 46thly, double-check the results of the voltage drop calculation to ensure that they are reasonable. If the voltage drop seems too high or too low, re-examine the input data and the calculation process to identify any errors. 47thly, voltage drop is an important consideration in electrical system design and installation. By carefully calculating and managing voltage drop, you can ensure that electrical equipment receives the proper voltage for optimal performance and that the electrical system operates safely and efficiently.